There is a moment, probably familiar to you, when you are looking at something and you realize you have no idea what you are actually looking at. Not that the thing is hidden or obscure, that you have been using a word for years, pointing at a thing with that word, and the word and the thing have been getting along well enough that you never noticed they were not the same. The word was doing its job. The thing was sitting there. Nobody complained. The thing I want to talk about tonight is time, not the philosophy of time, which is its own long conversation that I am not prepared to have at this hour. The physics of time. The actual, measurable, experimentally confirmed fact that time is not what most of us think it is. That it does not flow at a fixed rate. That it is not the same for everyone. That a clock in one location runs at a genuinely different rate from a clock in another location. And this is not a metaphor, not a thought experiment, not a prediction sitting out in the future waiting to be tested. It is happening now. It is happening to every clock in the world right now, including whatever device you are using to read or hear this. This channel runs without ads, without institutional support. It is just me, research, and the people who have decided that this kind of late-night physics is worth their time. If you want to help keep it going, there's a Patreon in the description. Even a small contribution changes what is possible here. And the people who have already found their way to it, you are the reason this continues. I do not say that casually. Let me start somewhere specific. A GPS satellite orbits the Earth at an altitude of roughly 20,000 kilometers. It carries an atomic clock, a cesium or rubidium oscillator, keeping time to better than a nanosecond per day. The whole point of the system is precision. If the timing is wrong, the position calculation is wrong. 1 nanosecond of timing error translates to roughly 30 centimeters of position error. The system is designed around the assumption that the timing will be nearly perfect. Here is the problem. The satellite's clock does not agree with the clocks on the ground, not because of manufacturing defects or signal delays, because of physics. Two distinct effects conspire to pull the satellite's timekeeping away from the grounds. Special relativity predicts that a clock moving fast relative to an observer runs slow as seen by that observer. The satellite is moving at roughly 14,000 kilometers per hour relative to the surface. This causes the satellite clock to lose about 7 microseconds per day compared to a ground clock. 7 microseconds per day every day, accumulating without stopping. But there is another effect. General relativity predicts that a clock deeper in a gravitational well runs slower than a clock higher up. The satellite is far above the Earth's surface, higher in the gravitational field, and so, by general relativity, it gains about 45 microseconds per day compared to the ground clock. The two effects work in opposite directions. Special relativity says the satellite loses 7 microseconds. General relativity says it gains 45. The net is a gain of roughly 38 microseconds per day relative to the ground. 38 microseconds per day. That sounds small. It is not small in terms of what it does to a navigation system. Left uncorrected, the position error accumulates at roughly 11 kilometers per day. After a month, GPS would be useless for navigation. After a year, it would be telling you that you are in a different country. The engineers knew this. They accounted for it. The clocks on GPS satellites are deliberately set to run slightly slow before launch, so that once they are in orbit and the relativistic effects kick in, they end up running at the right rate. The correction is baked into the hardware. every time you navigate somewhere, every time you ask your phone where you are and it answers, the answer depends on a relativistic correction that would have seemed like pure abstraction in Newton's time. I am drinking tea that has gone lukewarm. I made it an hour ago and keep forgetting it. This happens when I sit down to write something about time, which I find either appropriate or too on the nose to mention, and am apparently mentioning anyway. The thing about the GPS example is that it is not just illustrative. It is not here to prove a point and then step aside while we talk about something more interesting. It is interesting precisely because it shows what time actually is, which is not a universal backdrop against which things happen, but a physical quantity that behaves differently depending on where you are and how fast you are moving. Time is not a stage. Time is a participant. Newton thought it was a stage. He was explicit about this. In the Principia, he wrote that absolute, true, and mathematical time of itself, and from its own nature, flows equally without regard to anything external. That is a clean sentence. It expresses clearly what most people still intuitively believe. Time is the same everywhere. Clocks measure it. The clocks might not be perfect, but the time they are measuring is universal and constant. Einstein dismantled this, not as a philosophical preference or a theoretical convenience, but because the evidence demanded it. The first blow came from special relativity in 1905. The second, heavier blow from general relativity in 1915. And the two together produce a picture of time that is so different from Newton's that it is honestly remarkable. We got as far as we did without noticing. Special relativity starts from two postulates. The laws of physics are the same in all inertial frames, meaning all frames moving at constant velocity relative to each other. And the speed of light in a vacuum is the same for all observers, regardless of how they or the source of the light are moving. The second postulate is the one that forces everything else. If light always moves at the same speed for every observer, and two observers are moving at different speeds relative to each other, something else has to give. That something is time. Imagine you are on a train moving at a significant fraction of the speed of light, and you are bouncing a beam of light between two mirrors, one on the floor and one directly above it on the ceiling. For you, the light is going straight up and straight down. Simple. The path length is just twice the height between the mirrors. Now, imagine someone standing on the platform, watching you pass. They see the mirrors moving sideways as the train goes by. They see the light not going straight up and down, but following a diagonal path, like the path of a thrown ball that travels forward as well as upward. The diagonal path is longer than the vertical path you measured, but the speed of light has to be the same for both of you. Speed is distance divided by time. If the distance is greater for the platform observer but the speed is the same, then the time has to be longer. More time has elapsed in the platform observer's accounting of your bouncing light than in yours. Your clock is running slow as far as the platform observer is concerned, not because of any defect in the clock, because of the geometry of what it means for time to pass when you are moving at high speed. This is time dilation. It is not a trick. It is not an illusion. A real clock carried at high speed genuinely records less elapsed time than a clock left behind. The amount of dilation depends on the speed. At everyday velocities, the effect is so small, it is completely undetectable without atomic clocks. At 10% of the speed of light, a clock runs about 0.5% slow. At 90% of the speed of light, it runs to less than half the rate of a stationary clock. At 99%, it is running at about 14% of the rate. At 99.9%, about 4.5%. The closer to the speed of light, the more dramatic the effect. There is a number that captures this, the Lorentz factor, usually written as gamma. It equals 1 divided by the square root of 1 minus the ratio of your speed squared to the speed of light squared. At everyday speeds, gamma is so close to 1 that it makes no practical difference. As speed increases toward the speed of light, gamma increases without bound. At the speed of light itself, gamma will be infinite, which is part of why nothing with mass can reach the speed of light. To do so, it will require infinite energy. The street light outside my window is doing something it does at irregular intervals. A faint pulse, not quite a flicker, more like a single, slow blink. I have been watching it happen intermittently for the last hour without deciding what to make of it. It has nothing to do with the Lorentz factor. I mention it only because I notice everything when I am trying to think about something difficult. And time at this hour feels like both the subject and the medium of the work. Here is the thing that I think gets underemphasized when people encounter special relativity for the first time. The time dilation is mutual. If you are on the train and I am on the platform, you see my clock running slow and I see your clock running slow. Both of us are right. This is not a contradiction. It is what it means for time to be relative rather than absolute. There is no fact of the matter about whose clock is running at the right rate in some cosmic sense. Rate is only defined with respect to something else. Both observations are valid from their respective frames. This becomes less symmetric when acceleration enters the picture, which is where special relativity hands off to general relativity. If you and I start together, you travel away at high speed, then turn around and come back, and we compare clocks, yours will show less elapsed time than mine. Not because your clock ran slow during the outbound and inbound legs, though it did, but because the turnaround required acceleration, and acceleration breaks the symmetry. This is the twin paradox, and it is not actually a paradox. It is just an asymmetry created by the fact that one of us changed direction and the other did not. The traveler ages less. The effect is real and verified. Muons, unstable particles produced by cosmic rays striking the upper atmosphere, have a half-life that should result in almost none of them reaching the ground before decaying. But they are detected at ground level in numbers that only make sense if their clocks are running slow at the velocities they travel. They live longer from our perspective because they are moving fast. Their time is dilated. The muons are the twins that left and came back, except they never come back. Their clocks just run slow the whole way down. General relativity adds gravitational time dilation on top of this. Mass curves spacetime, and the curvature affects the flow of time. Deeper in a gravitational field, time runs slower. Not slightly slower in some abstract sense. Measurably, verifiably, practically significantly slower. The clearest way I know to see why gravity affects time is through the equivalence principle, which Einstein called the happiest thought of his life. He realized that a person in free fall feels no gravity. They are weightless, just as an astronaut in orbit is weightless, not because the gravity has turned off, but because they are falling with it. There is nothing pushing back, nothing to resist the pull, and the absence of resistance is what the absence of a force feels like. You feel forces through their opposition. gravity, felt as a force, requires something pushing back. Now, flip this. A person in an accelerating rocket, accelerating upward at the same rate as the gravitational acceleration at Earth's surface, would feel exactly the same as a person standing still on Earth. The floor pushes up on their feet with the same force. Every experiment they do in the rocket gives the same result as the same experiment on the ground. The equivalence principle says this is not a coincidence. Gravity and acceleration are locally indistinguishable. Now imagine the rocket is accelerating, and someone at the bottom of the rocket shines a light upward toward the top. By the time the light reaches the top, the rocket has accelerated. The top is moving faster than it was when the light was emitted. By the Doppler effect, the light reaching the top will be redshifted. Its frequency will be lower. If frequency is lower, time is passing more slowly for the signal as seen from the top. The light arrives redshifted, carrying less energy, as if it had climbed out of something. Now, translate back to gravity through the equivalence principle. A gravitational field should produce the same effect. Light climbing out of a gravitational well should be redshifted. Time should pass more slowly deeper in the well. The bottom of the rocket corresponds to deeper in the gravitational field. The bottom clock runs slower. This was confirmed experimentally by Pound and Rebka in 1959, using two detectors separated by a height of just 22.5 meters, the height of a building. Using the Mossbauer effect to produce and detect gamma rays with extraordinary precision, they measured the gravitational redshift over a height of 22 meters and found it exactly where general relativity predicted. Gravity bends time at the scale of a building. The clock on your ground floor is running measurably slower than the clock on your roof. My tea has been forgotten again. It is properly cold now. There is something about this that I have stopped finding funny and started finding structurally interesting. Tea goes cold, and clocks run slow, and neither process announces itself while it is happening. You just look up and find it already done. The two effects together, kinematic time dilation from velocity and gravitational time dilation from position in a gravitational field, are what general relativity actually describes. They are not separate phenomena that happen to add up. They are both aspects of the same thing, which is that time is a dimension of a four-dimensional spacetime, and that spacetime is curved by mass and energy, and that the curvature changes how objects move through it, and that those objects include clocks, and that the clocks tick at the rate that the geometry allows. What this means for a black hole, which is where any serious conversation about time tends to end up, is something genuinely strange. The gravitational time dilation that produces a 38 microsecond per day correction for GPS satellites becomes extreme near a very massive object. Near a black hole, the gravitational field is so intense that the time dilation becomes enormous. As you approach the event horizon from outside, a distant observer watching you fall would see your clock run slower and slower, not just slower, asymptotically slower, approaching a complete stop. From the distant observer's perspective, you never quite reach the horizon. Your image slows and dims and redshifts toward invisibility. The last photons leaving you just before you reach the horizon take longer and longer to climb out of the increasingly deep gravitational well. They arrive at the distant observer stretched and depleted. Eventually, there are no more photons, not because you stopped, but because the remaining photons cannot escape. The information about your crossing is trapped, but from your own perspective, falling freely. Nothing unusual happens at the horizon. Your clock keeps running normally. Your thoughts keep moving. You cross the most consequential threshold in the physics you know, and the physics declines to acknowledge it. The crossing is a non-event, locally. Globally, it is the end of your causal connection to everything outside. This is the point I keep returning to when I think about what time dilation actually means. It is not just a correction factor you apply to satellites. It is a statement about the nature of time itself. Time is not external to the universe. Time is woven into the structure of the universe, into the geometry of space-time, and the geometry responds to what is in it. Put mass there and the geometry curves and the time nearby runs differently. Move fast through the geometry and your time runs differently. The time you experience is the time that the geometry allots to your particular path through it. There's a concept called proper time, which is the time measured by a clock that you carry with you, the time along your actual world line through space-time. It is what distinguishes your experience from someone else's experience. Two people can travel between the same two events, start and end in the same place at the same times in some sense, and their clocks can show different elapsed times depending on the paths they took. The person who took the longer path through space-time, in the four-dimensional sense, aged less. The geometry determines how much time passes for any given path. The twin that travels away and returns has taken a shorter path through space-time than the twin who stayed home. Not shorter in space, longer in space. Shorter in space-time. This is counterintuitive because we are used to thinking of spatial paths, where the shortest distance is the straight line. But in space-time, the geometry inverts this in a sense. The longest path in space, the one that goes out and comes back, corresponds to the shortest proper time. The twin who stayed home took the most direct path through time. The traveler took the scenic route through space and came back younger. I want to sit with the strangeness of this for a moment before moving on, because I think it is easy to absorb it intellectually and not actually feel the weight of it. Two people can share a moment, separate, and share another moment and genuinely, measurably, physically have experienced different amounts of time between them. Not different perceptions of the same time, different amounts of actual time, different lengths of life lived. If you could travel fast enough and come back, you could be biologically younger than your own children. This is not a thought experiment anymore. The muons do it every second they fall through the atmosphere. Haffel and Keating demonstrated it in 1971 by flying atomic clocks around the world on commercial aircraft and comparing them to clocks that stayed on the ground. The flying clocks show different elapsed time than the stationary ones. The amounts match the predictions of special and general relativity combined. Clocks on planes run differently from clocks on the ground. Every flight you have ever taken has returned you very slightly younger than if you had stayed home. The amount is negligible in any practical sense. The physics is not. The cold air from somewhere, a gap under the door probably, is making the paper on my desk drift in a way that is just on the edge of visible. It starts and stops. I keep noticing it between paragraphs. I mention it because the writing happens in a room at a specific hour, and that is part of what the writing is, not just the ideas, but the place they get assembled. Here is a harder version of the time dilation question. Not just that different clocks run at different rates, but what that means for simultaneity. In Newton's framework, two events are either simultaneous or they are not. There is a fact of the matter. Everyone who measures correctly will agree on whether they happened at the same time. In special relativity, this is gone. Simultaneity is relative. Two events that are simultaneous in one frame are not simultaneous in another frame moving relative to it. There is no privileged frame. No one's accounting of which events happened at the same time is more correct than anyone else's. This is not a small thing. It means there is no universal now. There is no moment that spans the universe and divides it into past and future in a way that everyone agrees on. Your now and my now, if we are moving relative to each other, do not coincide across large distances. For events separated by a light year, what I call happening right now and what you call happening right now, if we are moving apart at any significant speed, can differ by a year in either direction. The universe does not have a global present tense. It has a collection of local nows, each one valid for the observer who is moving with that particular velocity, none of them more true than any other. I find this more unsettling than most things in physics. The GPS correction and the muon lifetimes and the plane clocks are all confirmations of something that, once I sit with it, properly resists the idea of acceptance. Not cognitively. I can run the equations. But whatever part of the brain receives a statement as a real fact about the world, rather than a formal structure that predicts measurements, that part keeps defaulting to the Newtonian picture. The picture where there is a time and it flows, and we all experience the same version of it. That picture is wrong. It works for all everyday purposes, the way Newtonian mechanics works for all everyday purposes. It does not describe what is actually happening. What is actually happening is something I want to try to say in plain language, even though the plain language resists it. Space-time is a four-dimensional structure. 3 dimensions of space, 1 dimension of time. These dimensions are not independent in the way we intuitively treat them as independent. They are mixed together in a mathematical sense, in a way that depends on how fast you are moving. Moving faster through space means moving slower through time. Sitting still in space means moving as fast as possible through time. Everything moves through space-time at the same total rate, roughly speaking, the speed of light. You are always moving through space-time at the speed of light. If all your motion is through time, none of it through space, you experience the maximum rate of time. If you redirect some of that motion into space by moving fast, less is left over for time. You age more slowly. This is not the most rigorous way to say this, and a physicist reading it would have corrections to make. But it captures something real. Time and space are not separate things. They are aspects of a single structure, and that structure is what gets curved by mass and what gets navigated differently at different velocities. You do not move through space and through time. You move through space-time, and the path you take determines how much of each you experience. Outside, a car passes. I hear it before I see the light sweep across the ceiling. By the time the light reaches me, the car is already past. This is the most ordinary version of the same thing. The light from the car takes time to cross the distance. What I see is not where the car is, but where it was. All observation is like this. All light is old. The clock on the wall is showing me the position of hands that were there when the light left them, which was a finite time ago, even if that time is too small to matter. The universe only gives us the past. The present is always inferred. The question that feels natural at this point is whether time has a direction. whether the asymmetry between past and future is fundamental to time or a consequence of something else, because the equations of physics are almost entirely time-symmetric. Run them forward, they describe what happens. Run them backward, you get another valid solution. Newton's laws, Maxwell's equations, quantum mechanics, general relativity. None of them contain a preferred direction of time at the fundamental level. The laws themselves do not know which way time flows, and yet it clearly flows in one direction. Cups fall off tables and shatter. They do not spontaneously reassemble from shards. Heat flows from hot to cold. It does not spontaneously flow from cold to hot. Memories of the past exist. Memories of the future do not. The past is fixed. The future is open. The asymmetry is so pervasive that it defines the texture of experience, and it is not in the laws. The standard answer is entropy. The second law of thermodynamics says entropy increases. The number of possible arrangements of a system moves toward more disordered arrangements, because there are vastly more disordered arrangements than ordered ones. A glass falling off a table and shattering increases entropy. A shattered glass spontaneously reassembling would decrease it. The spontaneous reassembly does not happen, not because it is forbidden by any law at the level of particles, but because the probability is so fantastically small that it does not occur in any practical sense. The direction of time in this view is the direction of increasing entropy. The arrow of time points toward higher entropy. Why entropy was low in the past is a different question, one that points back to the initial conditions of the universe, to the fact that the Big Bang was a state of extraordinarily low entropy, and everything since has been the universe moving toward higher entropy, more disordered arrangements, more spread out energy, more ways for things to be. This is true, and it is also somehow incomplete, in a way I find difficult to pin down. The arrow of time is real, and its connection to entropy is real, and yet the statement that time flows because entropy increases has a strange quality. It explains the asymmetry of observable processes, without quite explaining what time itself is or why it has this dimension-like property that the others lack. There is a pen somewhere on this desk that I have been moving every time I shift papers and have now lost entirely. This happens. The desk is a process, not an object. The pen existed as a definite thing in a definite place, and now it is somewhere under something. This is entropy at the scale of a desk. I note it without editorial comment. Let me turn to something more concrete, the measurement of time. We have been talking about time as if it is something that can be measured, and of course it can. That is what a clock does. But what is a clock actually measuring, and how good can clocks get? Ancient clocks were astronomical. The sun crossing the sky, the shadow of a gnomon on a sundial, the stars wheeling overhead. These are good clocks at the level of days and years. They are terrible clocks at shorter intervals. Water clocks, pendulums, mechanical oscillators. Each improvement in precision came from finding a physical process that repeats more reliably and more quickly than the previous one. The invention of the quartz clock in the 20th century was a significant step. A quartz crystal in an electric circuit oscillates at a frequency determined by its size and cut, typically around 32,000 times per second. Electronic circuits count the oscillations and convert them to displayed time. A good quartz clock loses or gains about a second every few years. Atomic clocks are something else entirely. They use the quantum mechanical transition between two energy levels of an atom typically cesium-133, as their reference frequency. The definition of the second since 1967 has been exactly 9,192,631,770 oscillations of the radiation corresponding to the transition between the two hyperfine ground states of cesium-133. The second is not defined by astronomical motion. It is defined by quantum mechanics, by the fact that atoms in specific states absorb and emit radiation at specific frequencies that do not change from one cesium atom to another, or from one day to the next. A modern cesium atomic clock loses or gains about 1 second in 300 million years. That is not 30 years. That is 300 million years. Optical atomic clocks, which use transitions at much higher frequencies in atoms like ytterbium or strontium, are better still. The best of them are accurate to 1 second in several tens of billions of years. The age of the universe is about 13.8 billion years. These clocks are more accurate than the age of everything, and these are the clocks that measure gravitational time dilation directly. Place 2 of them at different heights in the same building, and they drift relative to each other in the way general relativity predicts. The taller one runs faster, measurably, precisely, in exact agreement with the theory. Time dilation is not a theoretical prediction awaiting confirmation. It is a confirmed fact measured in real clocks in real buildings. The significance of this precision extends beyond navigation and testing general relativity. Atomic clocks are sensitive enough to detect things that nothing else can detect directly. A sufficiently sensitive atomic clock can detect the presence of dark matter if dark matter couples to ordinary matter in ways that oscillate at appropriate frequencies. It can detect changes in fundamental constants if those constants are not actually constant but slowly drifting. It can detect the passage of gravitational waves through the slight variation they produce in local spacetime geometry. Time measurement has become a fundamental probe of physics. The most precise thing we can do is count oscillations of an atom. And because everything in physics ultimately connects to spacetime, and spacetime affects those oscillations, the atomic clock has become a window into questions far beyond timekeeping. There is something I find genuinely moving about this, that the quest to know what time it is, a quest that began with ancestors noting where the sun stood and turned into sundials and water clocks and pendulums and quartz crystals, ends in atoms absorbing and emitting quantum radiation at rates that probe the structure of spacetime and the constancy of fundamental physical law. The question has not changed. What time is it? Only the depth at which it is being asked. I have been sitting here for longer than I intended. The lamp that serves as the main light in this room is warm and slightly orange, the kind of light that was not designed for reading technical material, but which has become the light this work happens under by default. I think about this occasionally, whether the hour and the light shape the writing in ways I cannot fully account for. There is a harder question underneath the time dilation discussion that I have been circling and want to address directly. Is time real? Not in the everyday sense, where obviously yes, but in the deeper sense of whether time is fundamental to the universe or whether it emerges from something more basic. Physics has produced 2 great theories that together describe almost everything we can observe. General relativity, which describes gravity and the large-scale structure of the universe, treats time as a coordinate in a 4-dimensional space-time manifold. It is smooth, continuous, geometric. Quantum mechanics, which describes the behavior of particles and fields at small scales, treats time differently. It is an external parameter, not a dynamical quantity. The wave function evolves in time, but time itself is not described by quantum mechanics. It is assumed as a backdrop. When you try to put these theories together, as you must if you want to describe a black hole or the Big Bang, the two treatments of time conflict. General relativity wants to make time dynamical, part of the geometry that responds to what is in the universe. Quantum mechanics wants to treat it as a fixed external parameter. Reconciling them requires one to give way to the other, or both to give way to something deeper. Several approaches to quantum gravity, the theoretical framework that would unify the two, suggest that time is not fundamental, that it emerges from the quantum state of the universe in a way that is not yet fully understood. The Wheeler-DeWitt equation, which is the Schrödinger equation of the universe written in the language of general relativity, has no time in it. The wave function of the universe does not evolve in time. Time is not a variable. The equation is static. What this could mean, and opinions differ strongly on this, is that time as we experience it is an emergent phenomenon. That at the most fundamental level, the universe is a timeless structure. That the sense of time flowing, the distinction between past and future, the fact that we remember one direction and anticipate the other, all of this arises not from a fundamental temporal dimension, but from the entanglement structure of the quantum degrees of freedom, from the specific initial conditions of the universe, from the direction entropy is running. Time, in this picture, is like temperature. Temperature is real. You feel it. It does things. It governs physical processes. But it is not fundamental. It emerges from the collective behavior of many particles. There is no such thing as the temperature of a single particle. Temperature is a macroscopic description of microscopic disorder. Maybe time is analogous, real, measurable, governing everything you experience, and not in the basement of physics at the fundamental level. I genuinely do not know whether this is right. Nobody does. The approaches that suggest it are mathematically serious and pursued by serious people. They have not produced testable predictions that have been confirmed. The question of whether time is fundamental or emergent is open in a way that is not merely a gap in detail. It is open at the conceptual level. We do not yet have the right language to answer it. What I want to do with this, rather than leaving it as pure abstraction, is connect it back to what started us here: the GPS correction, the muon lifetimes, the plane clocks, the pound-Rebka experiment in a building. These are not just demonstrations of an equation. They are measurements of something physical. Whatever time is at the deepest level, whether fundamental or emergent, whether the Wheeler-DeWitt equation is telling us something profound, or whether it is an artifact of a wrong quantization procedure, the thing those clocks are measuring is real. The difference between the satellite clock and the ground clock is a real physical fact. 38 microseconds per day. Every day. Accumulated. Corrected for. Used. The theory that predicts this, general relativity, emerged from Einstein, asking what it would mean for the laws of physics to be the same for all observers, including observers in different gravitational fields and observers moving at different speeds. The answer turned out to require that time be not fixed, but geometrical, that the dimension of time be curved along with the dimensions of space, that clocks in different parts of the geometry tick at different rates, that the rate at which time passes is a physical quantity subject to physical variation. This was not an obvious step. Newton's absolute time was not an arbitrary assumption. It was forced by the assumption that gravity acts instantaneously, which it seemed to for 3 centuries of successful mechanics. Throw those 3 centuries at someone and ask them to give up absolute time, and they are right to be skeptical. The evidence that forced Einstein's hand was assembled carefully, and the theory it produced was checked carefully, and it passed every check. The thing that strikes me, sitting here at this hour with the lukewarm tea and the drifting paper and the lamp, is that none of this is finished. The GPS works, the predictions are confirmed, and yet the nature of time remains genuinely open at the deepest level. The emergent time question is not resolved. The reconciliation of general relativity and quantum mechanics is not complete. The question of what the Wheeler-DeWitt equation means for the reality of time is not settled. We have a theory that works. We have an understanding that we cannot see past. Both of these things are true at the same time. The working theory is extraordinarily precise. The understanding is genuinely limited. There is a gap between how well we can calculate and how well we understand. And in that gap sits the question of what time actually is at the level beneath the geometry. I want to spend a moment on time travel because it comes up whenever time dilation does, and because the relationship between the two is not what most people expect. Time dilation is real and verified. Time travel is more complicated. Going forward in time faster than others is real. The traveling twin who returns younger than their sibling has done a version of this, not by arriving in the future instantaneously, but by aging less while their sibling aged more. If you traveled at 99% of the speed of light for what felt to you like 10 years, and then came back, you would find that much more than 10 years had passed on Earth. Exactly how much depends on the speed. This is travel to the future. It is not symmetric. You cannot come back to where you started in time. Going backward in time is a different matter. Nothing in special relativity permits it. Nothing in general relativity forbids it. In principle, there are solutions to Einstein's equations called closed, time-like curves that loop through time in a way that would allow someone to arrive before they departed. The most famous involves a rotating mass, the Gödel rotating universe solution, which Gödel presented to Einstein as a birthday present. These solutions exist mathematically. Whether they can exist physically is deeply contested. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent closed time-like curves from forming, or to prevent anything from traversing them if they do. The motivation was partly physical intuition and partly the disturbing causal paradoxes that backward time travel permits. If you travel to the past and prevent your own departure, which version of events is real? The usual resolution offered is that paradoxes cannot form because the universe self-consistently prevents them. But how? Through what mechanism? This has not been established. What can be said is that no experiment has ever detected backward time travel. No verified signal has ever arrived before it was sent. Every observation is consistent with time flowing in one direction. The physics does not explicitly forbid closed time-like curves in all solutions, but no physical route to creating them has been identified, and the conditions that would be required, rotating masses of extraordinary density or wormholes stabilized by exotic matter, are either absent from our universe or unrealizable with any conceivable technology. The honest summary on backward time travel is that it is not ruled out by the equations and not supported by any observation and not achievable by any known means, which is a strange combination, but it is the current state. Something just shifted in this room, a sound from somewhere in the building. I am not going to speculate about what it was. I mention it because it is one of those moments where the present asserts itself against the work, which has been happening in some other time entirely, the time where the GPS satellites are running their corrections, and Einstein is having his happiest thought, and the muons are falling through the atmosphere. The present is louder than it looks. There is one more aspect of time that I want to address, and then I will let the night go. The question of why time seems to flow, why it seems to pass rather than simply being there, all of it at once, in the four-dimensional block that the physics implies. The block universe view, which follows fairly directly from special relativity, is that past, present, and future all exist equally as parts of a four-dimensional spacetime. The word now is a local label, meaningful for a particular observer at a particular point, but not a global fact about which part of the universe currently exists and which does not. Your past and your future are both equally real in the space-time, equally present in the geometry. What you experience as the present moving through time is your world line moving through the block. In this picture, the experience of time flowing is something that happens inside the geometry, not something the geometry does. The block does not flow. It is. But the observers inside it, the things with memories and anticipations, experience the sequence of moments as a passage, the experience of duration, of before and after, of time passing, arises from having a certain kind of relationship to the space-time, from being an entity with memory that extends in one temporal direction and anticipation that extends in the other. This is deeply strange if you sit with it properly. Every moment of your life is equally real in the four-dimensional block. The version of you that existed 10 years ago is not gone. It exists at its location in space-time with the same reality as the version of you reading this now. You cannot access that version. It is causally disconnected from you in the relevant sense, but it is there in the geometry, as real as the geometry is. Whether this is true depends partly on what we mean by real, and partly on unresolved questions about the interpretation of quantum mechanics. In quantum mechanics, the wave function describes superpositions of possibilities before measurement. After measurement, only one outcome is realized. Whether the other outcomes continue to exist in some sense, in branching worlds or a many-worlds structure, or whether they genuinely cease to exist, determines whether the block universe of space-time contains all quantum outcomes or only the ones that became actual. This is one of the deepest open questions in the foundations of physics, and it has been open since the 1950s. What I keep coming back to at the end of this is the GPS satellite. I started there because it is concrete. It is functioning right now. The correction is running right now. The 38 microseconds per day is accumulating right now and being corrected for right now by systems that depend on it being corrected. The relativistic effects are not waiting to be confirmed. They are being accounted for every second in infrastructure that a significant fraction of human activity depends on. The physics that required us to redesign clocks on satellites because Newton was wrong about time, that physics is the same physics that produces the frozen observer at the black hole horizon, the same physics that connects the muon lifetime to the Lorentz factor, the same physics that makes atomic clocks measure the height of a building. It is one continuous fabric. Time is woven into it, not as a passive dimension, but as a dynamical one. It responds to mass. It responds to velocity. It curves along with space. Let me try to go somewhere more specific, because I have been moving through the conceptual landscape of time dilation, and I want to spend time with the actual numbers. Not the 38 microseconds per day, because I have already leaned on that enough. The numbers that come from cosmology, from what the universe's expansion tells us about time at the largest scales. The universe is expanding. The galaxies are moving apart, not because they are flying through space from a central point, but because the space between them is growing. The metric of spacetime is changing at cosmological scales. There is a rate associated with this expansion called the Hubble constant, named after Edwin Hubble, who first measured the relationship between galactic distance and recession velocity in 1929. Its current value is somewhere around 70 kilometers per second per megaparsec. What this means is that for every megaparsec of distance between 2 points, which is about 3.25 million light-years, those 2 points are moving apart at 70 kilometers per second. A galaxy 3 megaparsecs away is receding at around 210 kilometers per second. A galaxy 50 megaparsecs away at around 3,500 kilometers per second, and so on. The expansion of the universe is itself a time dilation of a kind. Light from distant galaxies reaches us, red-shifted not only because the galaxies are moving away, but because the space the light traveled through has expanded while the light was in transit. The wavelength of the light stretches as the space stretches. A photon that was emitted by a galaxy when the universe was half its current size has had its wavelength doubled by the time it reaches us. It is redshifted by a factor of 2. We say the redshift z is 1. This cosmological redshift is related to time in a specific way. A galaxy at redshift 1 is not just far away. It is old. The light we are seeing left it when the universe was about half its current age. We are looking at the galaxy as it existed roughly 6 or 7 billion years ago. The farther away, the older. The highest redshift objects we can see, galaxies at redshift 10 or more, emitted their light when the universe was less than 500 million years old. Looking at them is looking back 9/10 of the way through cosmic history. The most distant light we can see is the cosmic microwave background, the thermal radiation from the early universe that I have mentioned in other episodes of this series. It has a redshift of roughly 1100. The universe, at the time of emission, was about 1100 times smaller than it is now in linear scale. The light has been traveling for about 13.4 billion years. It is not light from a galaxy. It is light from the universe itself, from before galaxies existed, from the era when the universe first became transparent and photons could travel freely for the first time. There is a horizon associated with this, a limit to how far we can see, not because the universe ends there, but because light from farther away has not had time to reach us. The observable universe has a radius of about 46.5 billion light-years. This seems larger than the age of the universe in light-years, because the universe has been expanding the whole time the light was traveling. The light that has been traveling for 13.8 billion years started from regions that are now 46 billion light-years away. Beyond the observable horizon, there is more universe. How much, we cannot say. The simplest models suggest that it extends far beyond what we can see. Some models suggest it is infinite. What lies beyond our horizon is not hidden in the way a black hole interior is hidden. It is hidden by the finite speed of light and the finite age of the universe. Given enough time, more of it will become visible. The horizon is expanding, slowly, as the universe ages and light from more distant regions has time to arrive. But the expansion of the universe complicates this. For sufficiently distant regions, the space between us and them is growing faster than light can cross it. They are receding faster than light. Not because they are moving through space at superluminal speeds, but because enough space is opening between us that the recession velocity calculated from the expansion rate exceeds the speed of light. Regions beyond a certain distance, the Hubble sphere at roughly 14 billion light-years, are receding faster than light. Light emitted from them right now will never reach us. The space between us and them grows faster than the light can traverse it. This is different from the event horizon of a black hole in its cause, but similar in its effect. There is a surface beyond which causal contact is not possible. The cosmic event horizon, which for our universe sits at roughly 16 billion light-years and is determined by the details of how dark energy drives the acceleration of expansion, marks the boundary beyond which any signal sent now will never reach us. Galaxies currently beyond that horizon, which is a large fraction of the observable universe, have already sent their last signal that will ever reach us. We are already causally disconnected from most of what we can currently see. We just have not received the disconnection yet. The last photons from those galaxies are on their way. After them, nothing. I have written myself into a corner by pointing out that most of the observable universe is already beyond the point of causal reach. Let me find a way out that is not merely depressing. The corner leads somewhere actually interesting. The fact that the universe has a horizon, that expansion limits what we can ever interact with, is itself a kind of time asymmetry. The early universe, more compact, had a smaller horizon. Everything that would become the observable universe was in causal contact, or very nearly so. As the universe ages and expands, the horizon grows in one sense, but the number of things within causal reach shrinks. The future is less connected than the past was. There's a lecture by physicist Sean Carroll that I have thought about periodically for years. The central point was that the arrow of time, entropy increasing, past being low entropy, and future being high entropy, traces back to the initial conditions of the universe. The Big Bang was a state of extraordinarily low entropy, not because it was simple, it was small and dense and hot, but because the distribution of matter was nearly smooth, and smoothness in a gravitational system is low entropy. Gravity likes clumping. A universe where matter is smoothly distributed is not the natural equilibrium of a gravitational system. The equilibrium is black holes and heat death. Everything either collapsed or dispersed to maximum disorder. The smooth early universe was the starting point far from equilibrium. Everything since has been the universe relaxing toward that equilibrium. Stars forming from slightly denser regions. Stars fusing their hydrogen and radiating energy. Stars dying and leaving remnants. Galaxies colliding and merging. The smooth early universe collapsing under gravity into all the structure we see. Each step increases entropy. Each step moves further from the low entropy beginning. The arrow of time is the direction of this relaxation. What explains the low entropy beginning is not clear. It might be that the universe tunneled into existence from a quantum vacuum in a specific low entropy state. It might be that inflation smoothed out the initial conditions in a way that enforced low entropy. It might be something about quantum gravity that we do not yet understand. The question is open and uncomfortable, because the second law of thermodynamics, combined with any explanation of the Big Bang, tends to imply that there was something before the Big Bang, in an even lower entropy state, or that the low entropy beginning was in some sense extremely improbable, and we are here because of an anthropic selection for a universe capable of producing complex structure, which is not an explanation so much as a restatement. I am aware that I have been writing for a long time, and that the window of reasonable late-night attention is finite. The paper on my desk has stopped drifting. Either the gap under the door is sealed now, or the air in the room has settled. There is a quality of stillness that comes late enough, where the sounds from outside have dropped below a threshold, and what remains is the small mechanical noises of the house, the refrigerator, the occasional creak of a beam. I find it easier to think in this than in noise, though not because the thinking requires silence, because silence at this hour has a specific texture that feels appropriate to this kind of material. The big, slow questions of physics, the ones with no quick answer, need time around them. Let me come back to atomic clocks, because I want to stay with what they are telling us about time. The current frontier is not the cesium clock. It is optical atomic clocks, using transitions in atoms like ytterbium or strontium or aluminum ions. These transitions happen at frequencies in the visible or near-visible part of the spectrum, hundreds of trillions of oscillations per second compared to 9 billion for cesium. More oscillations means a finer clock tick, means higher precision. The best optical lattice clocks, in which many atoms are held in a grid formed by intersecting laser beams and interrogated simultaneously, have achieved fractional frequency uncertainties of around 1 part in 10 to the 18th. This means they would neither gain nor lose a second in about 30 billion years. Longer than the current age of the universe by more than a factor of 2. These clocks are not just measuring time. They are probing physics. Place 2 of these clocks at slightly different heights, and you can measure the gravitational redshift with a sensitivity that lets you detect a height difference of 1 centimeter. 1 centimeter of elevation. The general relativistic effect of a 1 centimeter height difference is a frequency change of about 10 to the negative 19th, and these clocks can measure it. The theory has not just been confirmed at GPS altitudes of 20,000 kilometers. It has been confirmed at the scale of 1 centimeter. This precision opens possibilities that are genuinely exciting to think about. An optical clock network, multiple clocks distributed across the Earth and connected by optical fiber links, could track variations in the gravitational field of the Earth with extraordinary sensitivity. Movements of groundwater, the accumulation of snow in mountain ranges, magma movements beneath volcanoes, the tiny changes in the local gravitational potential caused by mass redistributing near the surface would be readable in the differences between the clocks. Geodesy, the measurement of the shape and gravity of the Earth, would become a real-time continuous measurement with sensitivity that current instruments cannot approach. More speculatively, sufficiently precise clocks might detect the passage of gravitational waves directly, not through the kilometer-scale arm length of LIGO, but through the slight modulation in the local space-time metric that a gravitational wave produces. The effect would be tiny, but in the regime where optical lattice clocks operate, it might eventually be accessible. Or dark matter. If dark matter is a light scalar field that oscillates at some frequency and couples weakly to ordinary matter, the coupling would appear as a slight oscillation in the frequencies of atomic transitions. Different atoms couple differently to the scalar field. Comparing two different atomic species should reveal the oscillation if it is there. No convincing signal has been found yet, but the clocks are getting more sensitive, and the parameter space of possible dark matter properties is being narrowed. The thing about these precision searches is that they require understanding general relativistic effects at the same level of precision as the thing being searched for. You cannot look for a part per quintillion deviation in an atomic frequency if you have not correctly accounted for the gravitational time dilation of the clock's position at the part per quintillion level. The search for new physics requires mastering the known physics to greater precision than the new physics you are trying to see. General relativity is not background, it is foreground. There is a measurement that I think about in this context, which is the test of the equivalence principle using atomic interferometry. The equivalence principle, that the gravitational and inertial mass of an object are equal, that gravity pulls everything at the same rate regardless of composition, is one of the foundations of general relativity. Newton knew about it. Galileo allegedly demonstrated it. But it has a domain of applicability that classical tests cannot fully probe. In quantum mechanics, particles have a wave nature. They have a wavelength, and they interfere with themselves. An atom dropped in a gravitational field and an atom launched upward and falling back can be made to interfere with each other, and the interference pattern depends on the phase accumulated along each path, which depends on the gravitational acceleration experienced. If two different species of atoms fall at slightly different rates because of some violation of the equivalence principle, the interference pattern will shift. Atom interferometers are now sensitive enough to test the equivalence principle at the level of a few parts in 10 to the 15th. No violation has been found. The equivalence principle holds to extraordinary precision. What this means for the status of general relativity is that every test we can currently perform confirms it. GPS, atom interferometry, optical clock height measurements, gravitational wave detections, the shadow of the black hole at M87, binary pulsar timing, where the orbital decay of two neutron stars spiraling together matches the general relativistic prediction of energy loss to gravitational waves to better than 1 part in a million. None of these tests has shown a deviation from Einstein's theory. This is both satisfying and slightly uncomfortable. Satisfying because the theory is extraordinarily precise and extraordinarily well confirmed. Uncomfortable because we know the theory is incomplete. We know it breaks down at singularities. We know it cannot be reconciled with quantum mechanics without some modification. A theory that passes every test we give it while being known to be incomplete is one whose failures are precisely in the places we cannot test. The failures are in the black hole interior and in the Planck scale physics of the Big Bang. Everywhere accessible to measurement, it works. In the inaccessible places, it fails. There is something about this arrangement that feels deliberately inconvenient. The question this leaves, which is the one I find hardest to fully let go of, is whether the time that general relativity describes, the time that runs slower near mass and slower at high speed, and is woven into a four-dimensional geometric fabric, is the last word on what time is. Or whether there is a level of description beneath the geometry, at the scale of quantum gravity, at the Planck length where space-time itself may break into something discrete and different, where the smooth, flowing manifold of general relativity dissolves into something else, and whether at that level time looks the same or different or absent altogether. We do not know. The question is being held open in the most honest sense, not as a mystery preserved for atmosphere, not as a comfortable resting place, as a genuine gap that people are working on with real mathematics in the present tense, and that the next generation of experiments at the frontier of precision may eventually provide data to address. Every clock in the world is ticking right now, each one ticking at the rate the geometry allows it. The satellite clocks running slightly fast and being corrected. The clocks on the ground running at their rate. The clocks at the bottom of deep wells running fractionally slower. The time keeping by every atom in your body, ticking to the beat of the local space-time. All of it consistent, all of it geometrical, all of it more interesting than Newton thought. The universe is measuring something when it measures time. We are only beginning to understand what. Sleep well. If this kind of work in the quiet hours is worth something to you, the Patreon link is in the description. It is what keeps this going. Thank you for spending this time here, for what that is worth, from inside a universe where time does not quite mean what we thought it did.